Chapter 4. The Orient after the decline of Greek society. The Orient after the decline of the Greek society. The ancient civilization of the Near East never disappeared despite all Hellenistic influence. Both Oriental and Greek influences are clearly revealed in the science of Alexandria. Constantinople and India were also important meeting grounds of East and West. In 394, Theodosius I founded the Byzantine Empire. Its capital, Constantinople, was Greek, but it was the center of administration of vast territories where the Greeks were only a section of the urban population. For 1,000 years, this empire fought against the forces from the east, north, and west, serving at the same time as a guardian of Greek culture and as a bridge between the Orient and the Occident. Mesopotamia became independent of the Romans and Greeks as early as the 2nd century AD. First under the Parthian kings, later under the purely Persian dynasty of the Sasanians in 266. The Indus region had for some centuries several Greek dynasties, which disappeared by the 1st century AD. However, the native Indian kingdoms which followed kept up cultural relations with Persia and the West. The political hegemony of the Greeks over the Near East disappeared almost entirely with the sudden growth of Islam. After 622, the year of the Hegira, the Arabs conquered large sections of Western Asia in an amazing sweep, and before the end of the 7th century had occupied parts of the West Roman Empire as far as Sicily, North Africa, and Spain. Wherever they went, they tried to replace the Greco-Roman civilization by that of Islam. The official language became Arabic instead of Greek or Latin. However, the fact that a new language was used for scientific documents tends to obscure the truth that under Arabic rule a considerable continuity of culture remained. The ancient native civilizations had even a better chance to survive under this rule than under the alien rule of the Greeks. Persia, for instance, remained very much the ancient country of the Sasanians despite the Arabic administration. However, the contest between the different traditions continued, only now in a new form. Throughout the whole period of Islamic rule, there existed a definite Greek tradition holding its own against the different native cultures. We have seen that the most glorious mathematical results of this competition and blending of Oriental and Greek culture during the heyday of the Roman Empire appeared in Egypt. With the decline of the Roman Empire, the center of mathematical research began to shift to India and later back to Mesopotamia. The first well-preserved Indian contributions to the exact sciences are the Siddhantas, of which one, Surya, may be extant in a form resembling the original one from around 300 to 400 AD. These books deal mainly with astronomy and operate with epicycles and sexagesimal fractions. These facts suggest influence of Greek astronomy, perhaps transmitted in a period antedating the Almagest. They also may indicate direct contact with Babylonian astronomy. In addition, the Siddhantas show many native Indian characteristics. The Surya Siddhanta has tables of signs called ja instead of chords. This sign is a half chord, hence a line segment. The results of the Siddhantas were systematically explained and extended by schools of Indian mathematicians, mainly centered in Ujjain, central India, and Mysore, South India. From the 5th century AD, names and books of individual Indian mathematicians have been preserved. Some books are even available in English translations. The best known of these mathematicians are Aryabhata, called the first around 500, and Brahmagupta around 625. The whole question of their indebtedness to Greece, Babylon, and China is a subject of much conjecture. However, they show at the same time considerable originality. Characteristic of their work are the arithmetical algebraic parts, which bear in their love for indeterminate equations some kinship to Diophantus. These writers were followed in the next centuries by others working in the same general field. Their works were partly astronomical, partly arithmetic algebraical, and had excursions into mensuration and trigonometry. Aryabhata the first had for pi the value 3.1416. A favorite subject was the finding of rational triangles and quadrilaterals, in which Mahavira of the Mysore school around 850 was particularly prolific. Around 1150 we find in Ujjain, where Brahmagupta had worked, another excellent mathematician, Bhaskara taught the first general solution of indeterminate equations of the first degree. like a x plus b equals c, where a, b, c are integers, is found in Brahmagupta. It is therefore, strictly speaking, incorrect to call linear indeterminate equations Diophantine equations, where Diophantus still accepted fractional solutions. The Hindus were only satisfied with integer solutions. They also advanced beyond Diophantus in admitting negative roots of equations, though this may again have been an older practice suggested by Babylonian astronomy. Bhaskara, for instance, solved x squared minus 45 times x equals 250 by x equals 50 and x equals negative 5. He indulged in some skepticism as to the validity of the negative root. His Lilavati was for many centuries a standard work on arithmetic and mensuration in the East. The Emperor Akbar had it translated into Persian in 1587. In 1832, an edition was published in Calcutta. Ancient India may still yield many more mathematical treasures. We now know, for instance, that the Gregory Leibniz series for pi divided by 4 can already be found in a Sanskrit manuscript ascribed to Nilakantha around 1500. The best-known achievement of Hindu mathematics is our present decimal position system. The decimal system is very ancient, and so is the position system. However, their combination appears in China and then in India, where in the course of time it was gradually imposed upon older non-position systems. Its first Indian occurrence is on a plate of the year 595, where the date 346 is written in decimal place value notation. The Hindus long before this epigraphic record had a system of expressing large numbers by means of words arranged according to a place value method. There are early texts in which the word sunya, meaning zero, is explicitly used. The so-called Bakshali manuscript, consisting of 70 leaves of birch bark of uncertain origin and date, with estimates ranging from the 3rd to the 12th century AD, and with traditional Hindu material on indeterminate and quadratic equations as well as approximations, has a dot to express zero. The oldest epigraphic record with a sign for zero dates from the 9th century. This is all much later than the occurrence of a sign for zero in Babylonian texts. The sign O for zero may be due to Greek influence, since Auden is Greek for nothing, where the Babylonian dot only appears between digits. The Indian zero also appears at the end, so that 0, 1, 2, 3 and so on, up to 9 become equivalent digits. Brahmagupta states somewhere in his book that some of his problems were proposed simply for pleasure. This confirms the fact that mathematics in the Orient had long since evolved from its purely utilitarian function. 150 years later, Alcuin in the West wrote problems for the quickening of the mind of the young, expressing a similar non-utilitarian purpose. Mathematics in the form of the intellectual puzzle has often contributed essentially to the progress of science by opening new fields. Some puzzles still await their integration into the main body of mathematics. The decimal place value system slowly penetrated, probably originally from China, along the caravan roads into many parts of the Near East, taking its place beside other systems. Penetration into Persia, perhaps also Egypt, may very well have happened in the Sasanian period, from 224 to 641, when the contact between Persia, Egypt, and India was close. In this period, the memory of the ancient Babylonian place value system may still have been alive in Mesopotamia. The oldest definite reference to the Hindu place value system outside of India is found in a work of 662, written by Severus Sebokht, a Syrian bishop, with Al-Fazari's translation of the Siddhantas into Arabic around 773. The Islamic scientific world began to be acquainted with the so-called Hindu system. This system began to be more widely used in the Arabic world and beyond, though the Greek system of numeration also remained in use as well as other native systems. Social factors may have played a role. The Oriental tradition favored the decimal place value method against the method of the Greeks. The symbols used to express the place value numerals show wide variations, but there are two main types: the Hindu symbols used by the Eastern Arabs and the so-called Gobar numerals used in Spain among the Western Arabs. The first symbols are still used in the Arab world, but our present numeral system seems to be derived from the Gobar system. There exists the theory of Waqf, according to which the Gobar numerals were in use in Spain when the Arabs arrived, having reached the West through the Neo-Pythagoreans of Alexandria as early as the year 450. Mesopotamia, which under the Hellenistic and Roman rules had become an outpost of the Roman Empire, reconquered its central position along the trade routes under the Sasanians, who reigned as native Persian kings over Persia in the tradition of Cyrus and Xerxes. Little is known about this period in Persian history, especially about its science. However, the legendary history, as reflected in the 1001 Nights, Omar Khayyam and Ferdowsi, confirms the meager historical record that the Sasanian period was an era of cultural splendor. Situated between Constantinople, Alexandria, India, and China, Sasanian Persia was a country where many cultures met. Babylon had disappeared, but was replaced by Seleucia Ctesiphon, which again made place for Baghdad after the Arabic conquest of 641. This conquest left much of ancient Persia unaffected, though Arabic replaced Pahlavi as the official language. Even Islam was only accepted in a modified form known as Shia. Christians, Jews, and Zoroastrians continued to contribute to the cultural life of the Baghdad Caliphate. The mathematics of the Islamic period shows the same blend of influences with which we have become familiar in Alexandria and in India. The Abbasid caliphs, notably al-Mansur from 754 to 775, Harun al-Rashid from 766 to 809, and al-Ma'mun from 813 to 833, promoted astronomy and mathematics. Al-Ma'mun even organized at Baghdad a house of wisdom with a library and an observatory. Islamic activities in the exact sciences, which began with al-Fazari's translation of the Siddhantas, reached their first height with a native from Khiva, Muhammad ibn Musa al-Khwarizmi, who flourished around 825. Muhammad wrote several books on mathematics and astronomy. His arithmetic explained the Hindu system of numeration, although lost in the original Arabic. A Latin translation of the 12th century is extant. This book was one of the means by which Western Europe became acquainted with the decimal position. The title of the translation, Algorithmi de Numero Indorum, added the term algorithmus, a Latinization of the author's name, to our mathematical language. Something similar happened to Muhammad's Algebra Dal, which had the title Hizab al-Jabra wal Muqabala. This literally means science of reduction and confrontation, probably meaning science of equations. This algebra, of which the Arabic text is extant, also became known in the West through Latin translations, and they made the word al-Jabra synonymous with the whole science of algebra, which indeed, until the middle of the 19th century, was nothing but the science of equations. This algebra contains a discussion of linear and quadratic equations, but without any algebraic formalism. Even the Diophantine rhetoric symbolism is absent. Among these equations are the three types characterized by x squared plus 10x equals 39, x squared plus 21 equals 10x, and 3x plus 4 equals x squared. These had to be separately treated as long as positive coefficients were the only ones which were admitted. These three types reappear frequently in later texts. Thus the equation x squared plus 10x equals 39 runs like a thread of gold through the algebras for several centuries, writes Professor L. C. Karpinski. Much of the reasoning is geometric. Muhammad's astronomical and trigonometrical tables, with sines and tangents, also belong to the Arabic works which later were translated into Latin. His geometry is a simple catalogue of mensuration rules. It is of some importance because it can be directly traced to a Jewish text of the year 150 AD. It shows a definite lack of sympathy with the Euclidean tradition. Al-Khwarizmi's astronomy was an abstract of the Siddhantas, and therefore may show some indirect Greek influence by way of a Sanskrit text. The works of Al-Khwarizmi as a whole seem to show Oriental rather than Greek influence, and this may have been deliberate. Al-Khwarizmi's work plays an important role in the history of mathematics, for it is one of the main sources through which Indian numerals and Arabic algebra came to Western Europe. Algebra.ars, until the middle of the 19th century, revealed its Oriental origin by its lack of an axiomatic foundation. In this respect, it sharply contrasted with Euclidean geometry. The present-day school algebra and geometry still preserve these tokens of their different origin. The Greek tradition was cultivated by a school of Arabic scholars who faithfully translated the Greek classics into Arabic. These included Apollonius, Archimedes, Euclid, Ptolemy, and others. The general acceptance of the name Almagest for Ptolemy's great collection shows the influence of the Arabic translations upon the West. This copying and translating has preserved many a Greek classic which otherwise would have been lost. There was a natural tendency to stress the computational and practical side of Greek mathematics at the cost of its theoretical side. Arabic astronomy was particularly interested in trigonometry. The word sinus is a Latin translation of the Arabic spelling of the Sanskrit word for sine. The signs correspond to half the chord of the double arc. Ptolemy used the whole chord, and they were conceived as lines, not as numbers. We find a good deal of trigonometry in the works of al-Battani, also known as Albatanius, from around 850 to 929. He had a table of cotangents for every degree, known as umbra extensa, as well as the cosine rule for the spherical triangle. This work by al-Battani shows that Arabic writers not only copied, but also contributed new results through their mastery of both Greek and Oriental methods. Abu al-Wafa, also known as al-Buzjani, from 940 to 997 or 998, derived the sine theorem of spherical trigonometry. He computed sine tables for intervals of 15 minutes of which values were correct in 8 decimal places. He introduced the equivalents of secant and cosecant, and played with geometrical constructions using a compass of one fixed opening. He also continued the Greek study of cubic and biquadratic equations. Al-Karki, who died around 1029, wrote an elaborate algebra following Diophantus. He had interesting material on surds, such as the formula square root of 8 plus square root of 18 equals the square root of 50, and the square root of 54 minus the square root of 2 equals the square root of 16. He showed a definite tendency in favor of the Greeks. His neglect of Hindu mathematics was such that it must have been systematic. We need not follow the many political and ethnological changes in the world of Islam. They brought ups and downs in the cultivation of astronomy and mathematics. Certain centers disappeared. Others flourished for a while, but the general character of the Islamic type of science remained virtually unchanged. We shall mention only a few highlights. Around the year 1000, new rulers appeared in northern Persia, the Seljuk or Selchuk Turks, whose empire flourished around the irrigation center of Merv. Here lived Omar Khayyam, around 1058 or 1048 to 1023 or 1124, known in the West as the author of the Rubaiyat in the Fitzgerald version from 1859. He was an astronomer and a philosopher. In his poetry, Omar wrote, "Ah, but my computations, people say, have squared the year to human compass, eh? If so, by striking from the calendar, unborn tomorrow and dead yesterday." Here Omar may have referred to his reform of the old Persian calendar, which instituted an error of 1 day in 5,000 years, or 1540, or 3070 years, according to different interpretations, whereas our present Gregorian calendar has an error of 1 day in 3,330 years. His reform was introduced in 1079, but was later replaced by the Muslim lunar calendar. Omar wrote an algebra, which represented a considerable achievement since it contained a systematic investigation of cubic equations. Employing a method occasionally used by the Greeks, he determined the roots of these equations as the intersection of two conic sections. He had no numerical solutions and discriminated, also in Greek style, between geometrical and arithmetical solutions, the latter existing only if the roots are positive rational. This approach was therefore entirely different from that of the 16th century Bolognese mathematicians, who used purely algebraical methods. Omar, in another book dealing with difficulties in Euclid, replaced the parallel axiom by a set of other propositions. Here he came to the figures now associated with the so-called hypotheses of the obtuse, acute and right angle, which now find their place in non-Euclidean geometry. He also replaced Euclid's theory of proportions by a numerical theory, in which he approached a theory of the irrational and the concept of the real number in general. After the sack of Baghdad in 1256 by the Mongols, a new center of learning sprang up near the same place at the observatory of Maraga, built by the Mongol ruler Hulagu for Nasir al-Din al-Tusi, also known as Nasir Eddin, who lived from 1201 to 1274. Here again arose an institute where the whole of Oriental science could be pooled and matched with the Greek. Nasir separated trigonometry as a special science from astronomy. His attempts to prove Euclid's parallel axiom following in the path of Omar Khayyam show that he appreciated the theoretical approach of the Greeks. Nasir's influence was widely felt later in Renaissance Europe. As late as 1651 and 1663, John Wallis used Nasir's work on the Euclidean postulate. Nasir also continued in Omar's tradition in his theory of ratio and the new numerical approach to the irrational. Another Persian mathematician, Jemshid al-Kashi, who died around 1436, showed a great versatility in numerical work comparable to that later reached by late 16th century Europeans. He solved cubic equations by iteration and by trigonometric methods, and knew the method now known as Horner's for the solution of general algebraic equations of higher order. This method generalizes the extraction of roots of higher order or ordinary numbers, and seems to point to Chinese influence. In his work, we find the binomial formula for a general positive integer exponent. Next to sexagesimal fractions, he uses decimal fractions with ease. For example, 25.07 times 14.3 is 357.501, and he has pi in 16 decimals. This all may indicate that the Chinese mathematics of the Sung dynasty had been penetrating deeply into the Islamic world. An important figure in Egypt was Ibn al-Haytham, also known as Al-Hazan, who lived from around 965 to 1039. He was the greatest Muslim physicist whose optics had a great influence on the West. He solved the problem of Al-Hazan, in which we are asked to draw from 2 points on the plane of a circle lines meeting at the point of the circumference, and making equal angles with the normal at that point. This problem leads to a biquadratic equation, and was solved in the Greek way by a hyperbola meeting a circle. Al-Hazan also used the exhaustion method to compute the volumes of figures obtained by revolving a parabola about any diameter or ordinate. 100 years before Al-Hazan, there lived in Egypt the algebraist Abu Kamil, who followed and extended the work of Al-Khwarizmi. He influenced not only Al-Karki, but also Leonardo of Pisa. Another center of learning existed in Spain. One of the important astronomers at Cordoba was Al-Zarqali, also known as Arzakal, who lived from around 1029 to 1087. He was the best observer of his time and the editor of the so-called Toledan planetary tables. The trigonometrical tables of this work, which was translated into Latin, had some influence on the development of trigonometry in the Renaissance. The Toledan tables themselves were followed by the Alphonsine tables, named after Alfonso, the 10th of Castile in the 13th century, which were for centuries authoritative. As to Chinese mathematics, it would be wrong to consider it as an isolated phenomenon, perhaps like the mathematics of the Maya. There always existed, at the very least from the time of the Han dynasty, contemporary to the Roman Empire, considerable commercial and cultural relations with other parts of Asia and even Europe. Indian and later Arabic science had their influence on China, and Chinese science in turn left its imprint on the science of other countries. We think, for instance, of the decimal position system and negative numbers, which may well have found their way from China into India. Indian influence on China may again be as old as the introduction of Buddhism into China in the 1st century AD, however. There is little or no evidence of Greek influence despite some parallel developments. The studies on the ratio of circumference and diameter of the circle, which are typical of the post-Han period, seem therefore to have been conducted independently of Archimedes. Liu Hui, author of an extant commentary on the 9 chapters in 263 AD, found by inscribed and circumscribed regular polygons that 3.14001 is less than pi, which is less than 3.1427. 2 centuries later, we find with Zhu Chongqi and his son not only a value of pi in 7 decimals, but also the values of 355 divided by 113 and 22 divided by 7. During the Tang dynasty, from 618 to 906, a corpus of the most important mathematical books was assembled for official use in the imperial examinations. It was in this period that printing began. Although the first printed mathematical books of which we have knowledge date from 1084 and later. In Event 15, a printed edition of the 9 chapters appeared. In a book written by Wang H. Xiao, tongue around 625 RT, we find a cubic equation more complicated than x cubed equals a in the 9 chapters. However, the period of greatest flowering of ancient Chinese mathematics was that of the Sung dynasty from 960 to 1279, and the early years of the Mongol dynasty of the Yuan, the great Khan of Marco Polo fame. Among the leading figures, we find Qin Zhisha, whose book dates from 1247 to 47. He developed the theory of indeterminate equations, a theory which had been gradually developed throughout the centuries. One of his examples can be written as x equals 32, modulus 83 equals 70, modulus 110 equals 30, modulus 135. Qin also dealt with the numerical solution of higher degree equations, as exemplified by negative x cubed plus 763,200 dx squared minus 40,642,560,000 equals 0. He solved such equations by generalizing the method of successive approximations, used already in the 9 chapters, for the extraction of square and cubic roots. In this method we now recognize the same operations known in our textbooks after W. G. Horner, who published it in 1819, apparently unaware that he had hit upon a method typical of 1,000 years of Chinese mathematics. Another mathematician of the Sung period is Yang Hu, who worked with decimal fractions and wrote them in a way which reminds us of our present methods. His book dates from 1261. One of his problems leads to 24.68 times 36.56 equals 902.3108. Yang Hui presents us with the earliest extant representation of the Pascal triangle, which we find again in a book around 1303, written by Chu Shiqi. Chu, considered the most important of this group of mathematicians, offers in his books the most accomplished presentation of the Chinese arithmetical algebraic computational method. He even extended the matrix solution of systems of linear algebraic equations to equations of higher degree, with several unknowns with methods that remind us of Sylvester in the 19th century. In the post-Sung period, mathematical activity continued but did not reach new heights. Speaking generally, we can say that in their ability to do complicated arithmetical and algebraic work, the Chinese mathematicians were not only comparable to their Indian colleagues and to those who wrote in Arabic, but that they occasionally served them as masters. For instance, the method of Horner and the work with decimal fractions can later be found in the books of Al-Kashi of Samarkand.